The aforementioned problem is to study the group Q mod Z, and in particular, show that every element has finite order. I really like this group. This group comes up in a lot of places as an interesting, kind of weird group for having some strange properties, and this is kind of one of them. This is a huge infinite group, right? Because, well, what are the elements of this group? The elements of this group are things of the form z plus p over q. So the integer part gets absorbed, and then what remains is a fractional part. Therefore, p over q ranges between 0 and 1, where 0 is a possibility, right? The coset of the identity, but 1, if there was a 1, we would absorb it into z. And so this proof is really simple. Actually, even though the group is really weird, here's the proof. In additive notation, what we would be doing to discuss order would not be exponentiation, but just multiplication. So z plus p over q, what do we get if I multiply this times q? Well, this becomes qz plus qp over q. Q times z, the integer part, right? That's just z again, right? This is absorbed into z, right? It's the integer part. Here, the q's cancel, and p is an integer, right? Because all of these rational numbers, right? pq are they don't have to be natural numbers. They can be they can be integers as long as q is not 0. And so p is also an integer. And so this is z, which is the same thing as ze, right? The identity of this quotient group. And so what this is showing is if p over q is in lowest terms, then the order of p over q in q mod z is q. And of course, if it's not in lowest terms, then the order divides q, right? For example, if you have 2 over 4, right, the order of that is actually just 2 because the real lowest terms is just 1/2, which is 2. Okay, I think that's probably a good place to stop for this one. That was quite quick, and I almost wonder if we shouldn't do one more. So I think why not? Let's do one more. We still have, some bandwidth in us, I expect.